Welcome. In this video, we're going to talk about multivariable functions. This is multivariable calculus after all, so it makes sense we talk about multivariable functions. And this is going to be one of several videos for this topic. Now, why are we looking at multivariable functions? Well, it turns out so many things in the world are described in terms of more than one variable at the same time. So, for instance, some very basic examples are, how about the area of a rectangle? A rectangle has a width, let's call that x, and a height, let's call that y. And to compute the area, we can use a function. The function, I might call it a for area, and it depends on both the width and the height. And how does it depend on them? Well, we all know that to get the area, we multiply them, the width times the height. And so that is the description of this function. Okay, what about another function? Volume of a box. Well, the box will have a width and a depth and a height. And how do I compute the volume? Well, I multiply width times depth times height, right? So the volume function I might call v. It's a function of each one of these three variables. And as we said, to compute the volume, I just multiply them together. So another very basic function, but it's a function of three variables this time. Another example I can think of is a more physics type example. If you're shooting a bow and arrow, you're going to aim that bow and arrow up into the air, right? And pull back on it with some force, and then you're going to let go, right? So what am I doing? What are the two parameters I need to think about? Let's ignore wind resistance. Well, the angle that I'm holding it up, and also the force that I'm pulling back with. So it's depending on two things, an angle theta and a force F. So here's our bow and arrow, right? And I've got some angle theta above the horizon, and I have some force that I'm exerting backwards on this string. And we know that the distance that the arrow travels, let's call that d, is going to depend on the angle and on the force. Now, what would this be? Well, I'm going to let you figure this out. This actually isn't difficult to derive using basic calculus. And so that's a really great exercise for you. Figure out what the expression for this function would be. One final example I can think of is a loan, right? You take out a loan. How much do you have to pay back? Well, that depends on two things. One, how much you took out, and two, how long you took it out for, right? So the amount you owe on a loan is dependent on those two parameters. So it's a function of two variables. Okay, so those are just some examples, just a few examples of multivariable functions in the real world. So let's talk about the first topic that we're going to study mathematically about these, and that is the idea of domain. But first, let's talk about what a function does. Now, when you're thinking about single variable functions, the ones you learn about in algebra, what do those do? They take a number and they spit out a new number. The number they take lives in the domain, and the number they spit out lives in the range. In fact, the domain is the set of inputs, the numbers that you can plug in, and the range is the set of numbers that you can get out. Now, in this case, we're thinking of multivariable functions. So instead of plugging in just a single number, we're plugging in more than one number, maybe 2 or 3 or 4 or 5. Now, whenever you have more than one coordinate that you're plugging in, you can think of these as points. And so a multivariable function can be thought of as a function of points. Or you can think of vectors this way. Vectors in standard position correspond to points in space. And so you can also think of a multivariable function as a function of vectors. So here's the idea for a multivariable function. It's going to take a point or a vector, and it's going to produce from that a real number. And I might call my function f. So it might take, if I'm working with a two-dimensional point, if it's a function of two variables, it's going to take an xy, and it's going to produce, the output is called f of xy. So if the dimensions of my rectangle were 2, 3, the output, the area of my rectangle would be f of 2, 3. And we know how to compute that. It's 2 times 3, it's 6. And so like I said, the domain is the set of things that you can plug in to your function that will produce a real number after you plug them in as an output. So let's look at some examples of functions and see if we can identify what their domains are. So the first function I want to look at is this one. So here's a function. Now what I need to think about to find its domain are what values of x and y can I plug into here and get a real number? Well, sometimes when thinking about the domain, it's useful to think, at least temporarily, what wouldn't work? You know, what would go wrong here? Well, one of the first things that should catch your eye is the square root. Lots of things can go wrong with square root, right? In particular, if the thing under the square root is negative, then we have a problem, right? Can't take the square root of a negative number and get a real number. So that tells us that this thing under the square root has to be non-negative. Now, notice I don't say positive, right? Because it could be 0. So I'm careful to say non-negative instead of positive. Those are subtly different things. So that's what we need to find the domain. We need to explore when this thing is non-negative. Okay, well, let's just use a little bit of algebra and solve this inequality. Well, you know, using a little bit of algebra here, I think you'll see pretty quickly that this is equivalent to this inequality. Now, what if this were an equals 4 instead of a less than or equal to 4? Well, then what we would have is the equation of a circle of radius 2. But because it's less than or equal to 4, I also should consider those values that are less than 4, like 3.9, 3.8, 2, 1. These are all circles of radius less than 2. So if you imagine all those circles, they would fill in the interior of this region. And that's what we call in mathematics a disk. So the disk is the interior of the circle. So this is a disk of radius 2. Okay? And what we're seeing here is the domain. This is the points in here are the points that when you plug them in to this function will produce a real number output. Whereas points that are out here on the outside, when you plug them in, will make a negative under the radical and therefore will not produce a real number output. So those are the things that are not in the domain. So there's two ways to write this down. One using set builder notation. Now notice how I did that. Set builder notation says to use these curly braces. So that defines a set. So whatever you write is going to be in between these curly braces, right? And then what you're going to do is you're first going to start off by writing down what are the things that you're talking about. We're talking about points. This is a function that takes two numbers as inputs. We can think of them as points, right? So x comma y, a point. And then this vertical bar, sometimes you'll see this replaced with a colon, same thing. This means such that. So I'm looking at all points x, y, such that what has to be true? Well, we need x squared plus y squared to be less than or equal to 4. So that describes this disk precisely. Another way to do this would be to describe it more geometrically, and that would be what we said before. So another way to write this down, so I'll write or here. An alternative way would be to say that this is the disk of radius 2 centered at the origin. Those are two equivalent ways of saying the same thing. Now I'd like to just take a moment and take a look at this function. All right, so let's go to calcplot3D and take a look at the graph. Okay, oops. Okay, fun with green screen. So I'll have calcplot3D graph this, and we'll talk about how to get a better idea of what these graphs look like in one of the future videos. And here we have it. this is what the graph looks like. You see the xy plane down there. Now it's also introduced a third variable, z. We need z as a third variable to represent the value of the function. So we not only have the inputs in the xy plane down here, but we also have for each input the value of the function at that input, and that is represented by the height of the graph. So one thing you'll notice right off the bat is that not every point in the xy plane has a corresponding piece of the graph above it. So for instance, this point over here, 0, 3 in the xy plane doesn't have a graph above it in the z direction. That's because it's outside of the domain, right? But points that are in that disk of radius 2 down here do have, let me see if I can turn on transparency. Yeah, now you can see that full disk down here. Those points do have a graph above them because they are in the domain. And so this is what we're looking at. It's actually the top half of a sphere, right? That's what that function's graph looks like. And the domain is just the set of points in the xy plane where we have a graph. Okay, let's look at a new function. I'll call this one g. So g of xy, function of two variables, and it's going to be y over x minus y. Okay, let's think about what its domain is. Now, sometimes when you're thinking about the domain, it is useful to think about what's not in the domain. Sometimes that's an easier way to go about it, and that's what we'll do here. So what could go wrong here? Well, you know, these, in the numerator and denominator, these are super nice expressions. These are polynomials, right, in x and y. So no issues there. Polynomials defined everywhere. What I do see an issue with is the division, right? When we divide, we have to be careful about dividing by 0. If I divide by 0, I don't get a real number. In fact, I don't get anything. It's not defined, right? So that's what I have to be careful of, and that's the only thing I have to be careful of here, right, is when the denominator's 0. So here's what we're looking at, is what's not in the domain. What's not in the domain is what happens when x minus y equals 0. Let's use a little bit of algebra here and write this like this, y equals x. So what we're going to graph here is what's not in the domain. Well, here we go. Here's the line y equals x. The domain is everything that's out here away from that line, right? Everything except that line is the domain. So that's what I'm going to write down. Let's use set builder notation like we did before first. So notice I make an open bracket. It's the set of all what? Well, I'm in the plane, so I'm looking at points x comma y. So everything I'm looking at has this form. So I'm going to start it like this, such that, so now I'm going to put restrictions on what the points could be. Well, I just need those points to not satisfy this equation, right? Because that's what it means to not be in the domain, right? So I need this not to be true. So the set of all points x, y such that y is not equal to x. There you go. Now we can also write this down geometrically like we did before, and I would write it like this. All points x comma y not on the line y equals x. So a very natural description of what's going on. Let's take a look at what this one looks like in CalcPlot 3D. All right, here's its graph. And again, same kind of thing going on. You're actually seeing the xy plane on the bottom there, and z is representing the values of the function. Look at this mess. Okay, what is going on? Well, it's hard to describe this in words, right? That's why we have this picture and this fancy graphing software. But if we look at it from above, we can see that line y equals x. Let me flip it in the more familiar position like this. There we go. So the y-axis is pointing up, the x-axis is pointing to the right, right? And you can see there's this line here. Now, the computer graphics software is not super precise, right? So it has a bigger gap than actually exists. Okay, but what we do see evidence of is the line y equals x right here, and we can see there's an issue. Now, what's going on? If I tilt this thing down, oh, I can see exactly what's going on. The height of the function, the height of the graph, the values of the function are going off to infinity as we approach that line y equals x, or negative infinity if we look down in the bottom, positive infinity up here. So we can see there's a limit problem, whereas with a limit as we approach that line y equals x, the values of the function either shoot off to positive infinity or shoot down to negative infinity. And on that line, they're not defined. Okay, let's take a look at another function. Here we're going to look at a function of 3 variables, and I'll call it h. Okay, so h is a function of x, y, and z, and it is the natural logarithm of x squared plus y squared plus z squared. So what is the domain here? Well, what do I need to be in the domain? Well, this is a polynomial, so no issues there. But log, yeah, log's got issues. You can't take the natural log of a negative number, and in fact, you can't take the natural log of 0 either. So what I need for x, y, and z is I need that this quantity inside of the logarithm be positive, strictly positive. So for the domain here, I need x squared plus y squared plus z squared to be positive. Now, let's think about this. I'm squaring all these and adding them up, so isn't it automatically positive? Well, almost, except for one possibility, right? When x, y, and z are all 0. If those are all equal to 0, then it's not positive. It's equal to 0, right? And that's the only thing that can make this not true. So therefore, the domain is really all points x, y, z except the point 0, 0, 0. So there we are, writing it down using set builder notation. If I were to write it down geometrically, I would write it like this. Right. All points x, y, z except 0, 0, 0. Or you could write the origin, except the origin, right? Okay, so that's this function. I would love to show you the graph of this in Calcplot 3D, but I can't. Why can't I? Think about it. What is a graph? A graph is the domain, which for the other functions was the xy plane, together with a third coordinate, z, right? And so the z represented the value of the function at each point in the domain. So we had to put those together to get the graph. Now here, the domain is 3-dimensional. And so to draw the graph, I would need to not only show you that, but also show you another coordinate representing the value of the function. How many dimensions is that? 3 plus 1, that's 4 dimensions now. Well, Calcplot 3D does a great job. I mean, it's called 3D, right? So it does a great job of depicting things in 3 dimensions. 4 dimensions, forget it. Like it's not. I don't think we can show you a meaningful picture of what this is, and Calcplot 3D isn't even set up to try to do that because it knows it'll fail. So, are there ways to visualize what the graph might look like? Yes, and we will look at those things later on. But right now, not going there. Okay, last up, I'm going to look at one more function, k of x, y, and this is going to be the function y minus 2x. Very simple function. Let's see, what could go wrong here? Are there any values of x and y that could cause problems? No, any numbers for x and y that I plug in here. I can do this computation. I can do this probably in my head, right? Give me any 2 numbers. I can compute this pretty quickly, right? So no issues here. It's not going to be undefined anywhere. So that means that all points are in the domain. In other words, the domain is all points, right? So here's what I would write. Now, what is that? Well, this is a fancy R, and it stands for, so R stands for the real numbers, right? When I write R2, it means the real numbers and another copy of the real numbers. That's the Euclidean plane. This is a symbol to represent the Euclidean plane. This is the set of all points. So it's silly to use set builder notation here when you could just write it as simply as this. So this is probably how you'd write it. I mean, if you did want to write it out in words, you could write this. All points x comma y. And yes, there is a notation for the three-dimensional, Euclidean three-dimensional space, R3. Euclidean four-dimensional space, R4, etc. Right? So that's the notation we use. Yeah, it's just an extension of this idea of real number line. To emphasize that we're talking about this particular object, we use two vertical lines on the left-hand side. Sometimes they call that blackboard bold because it's hard to write things bold on a blackboard, but this is a trick that you can use to still emphasize that something is, it's like bold, you know, but it's the best we can do given the surface we're writing on. Okay, so let's take a look at the graph of this one. All right, let's take a look. And here we go. Look at this. What is it? You probably could have recognized that if I just replaced the function with the variable z, that would just be the equation for a plane, right? And that's what you're graphing here. You're just setting z equals to whatever the function's expression is. And so, yeah, that makes a plane. And here's the plane that we're looking at. And as long as the plane's not vertical, it's defined for all values x and y. So that's why its domain was all points. So that's what we're looking at there. All right, well, that's all we're talking about in this video, domains of functions. So we'll move on and talk about some other topics in the next one.